welcome back to Calculus 1. So what I'd like to do now is to go back to talking about functions and reviewing the different things that we can do with functions that make them so useful in mathematics. So the great thing about functions that makes them useful in mathematics, and not just mathematics, but in applied mathematics, so applications in physics and engineering, in the sciences, in medical fields, in analyzing sociological trends and things like this, is that a function gives you a way to kind of say, well, for a given input, what is the output of this function? And so, just as a really simple example, we could say that the amount of money that a person gets paid is a function of the number of hours that they work, at least if they're paid hourly rather than being on salary or something like that. So in this case, you take the number of hours and it allows you to compute the amount of money that you're supposed to be paid. So that's an example of a function. Another example of a function might be perhaps we are dealing with a population of animals and we want to know how many animals there are at any given time. Well, given the time, there's a fixed number of animals. Some, maybe there's a population of 500 animals on an island in a given year or something. So the population is a function of the time. And so that's another example where functions are useful. Mathematically, though, functions become very useful for other reasons. And that's what we're going to be talking about today and the different things you can do with them. And by the way, I have obtained a larger whiteboard, so hopefully things will be a little bit easier to see. So, operations with functions. When you are dealing with operations with functions, you can do pretty much any arithmetic operation to them that you could do to numbers. And the idea is actually pretty straightforward. If we want to define a new function, f plus g, well, all I need to do is I need to tell you how to find the output for a given input. So the output, if you plug in x here, it's going to be f evaluated at x plus g evaluated at x. And so this is kind of a straightforward thing. It's, in a sense, I'm not sure what else you could think of to try to do here. It's really the only thing that sort of makes sense to do, because we want to define what it means to add two functions. We know how to add numbers, and the only numbers involved are the outputs from this input. So we add those outputs. And that's really what we're doing when we add together two functions. The thing is that you can often kind of simplify things where if I have an expression for f and an expression for g, I can often come up with an expression for f plus g. So, for example, if I have f of x is equal to 5 times x, and g of x is equal to x minus 1, well then, if I want to find f plus g evaluated at 2, there's a couple of different ways that I can do this. I could say this is equal to f evaluated at 2 plus g evaluated at 2. That's going to be 5 times 2 plus 2 minus 1. That's 10 plus 1, which is 11. But I could also say, well, as a general rule here, f plus g evaluated at some number x is going to be 5x plus x minus 1, which is just 6x minus 1. And then I can say, so f plus g evaluated at 2 is 6 times 2 minus 1. Well, once again, that just gives me back 11. So in terms of evaluating it at 2, both of these processes give me the same result. But if I want to work with what is f plus g, then using this form is probably the way to go. It's really the one that I want to use if I'm going to talk about this in general. Now, when we do this addition operation, we do need to be a little bit careful about the domain. And let me show you why we need to be careful about the domain, because it's maybe not totally obvious why there would be any issues with the domains. So the thing is, the domain of f plus g is the intersection of the domains of f and g separately. And this is important because, well, in some cases it's sort of obvious, but in other cases it's not necessarily obvious, and that is when we need to be a little bit careful. So to give you an example where it's sort of obvious, let's suppose that f of x is equal to 1 over x, and g of x is equal to the square root of x plus 3. Well, then f plus g, evaluated on x, is 1 over x plus the square root of x plus 3. And the domain here is pretty easily seen. Excuse me for 1 second while I block out a bit of the noise from the hallway. The domain here, you can kind of see, you can't put in x equals 0 because you divide by 0, and you can't have x less than -3 because you'd be trying to take the square root of a negative number. So the domain is going to be the set of x such that x is bigger than or equal to -3 and x is not equal to 0. Now, x not being 0, that's the domain of f of x. Bigger than or equal to -3, that's the domain of g of x. So this really is the intersection of those. It's all the numbers that satisfy both conditions. But those conditions are sort of obvious from this formula. Now, I want to show you a situation where it isn't so obvious from the formula. And in this case, let's suppose that f of x is equal to 1 over x again. And let's suppose that g of x is equal to 3x minus 1 over x. So the domains here are going to be x not equal to 0 and x not equal to 0. But if I were to write out f of x plus g of x to give myself f plus g evaluated at x, well, this would be 1 over x plus 3x minus 1 over x. And this looks like it comes out to be 3x, but that is only true when x is not equal to 0. This is undefined at x equals 0. Now, I hope you guys can see why this expression on the left here is not defined when x is equal to 0, even though the expression on the right-hand side is defined at x equals 0. And this equality is only true if both sides are defined. Now, as long as they're both defined, this equality is going to be true, but it's not always going to be the case that both sides here are defined, and that's kind of a problem. I mean, it's not really a major problem. It's definitely a fixable problem. It's something we can handle, no trouble. It's just we do have to take it into account, okay? So when I say it's a problem, I don't really mean like, oh, we're stuck. I just mean we have to be careful. And so what we want to be careful about is we can say f plus g of x is equal to 3x, provided that we specify that it has a domain, the set of all x, such that x is not equal to 0. Because as long as x isn't 0, then it is true that f plus g evaluated at x will be 3x, okay? If x happens to be equal to 0, then f plus g isn't defined. So f plus g of 0, that's not defined, and that's fine. Functions don't have to be defined for all numbers. But the formula that we've used looks like it would be defined for 0, and that's why we do need to specify the domain carefully here. Now, I'm going to give you guys one of these types of things to think about for yourselves for a moment, and once I write this down, I encourage you pause this, think about it for a minute, make sure you understand what's going on. So what would be the domain of f plus g of x? And while you're finding the domain, also find the expression for f plus g of x given f of x is going to be equal to 1 over x plus 1 minus x, and g of x is going to be equal to the square root of x plus 2 minus 1 over x plus 1. Okay, so there you go. Pause this, take a minute to think about this, and then keep going, and we'll work it together. Okay, so hopefully you were able to figure that out. Let's take a quick look at how you actually do this problem. So I'm going to combine these together to get the expression first of all. So f plus g of x is going to be equal to 1 over x plus 1 minus x plus the square root of x plus 2 minus 1 over x plus 1. And the thing is, this simplifies to the square root of x plus 2 minus x. These two fractions cancel each other out as long as x is not equal to negative 1. So as long as this doesn't break the fraction, these two sides are going to be equal to each other. But we do have to worry about breaking that fraction. So the way that we find this final domain really is we can think about the domain of f here as being x not equal to negative 1, and the domain of g here is going to be x bigger than or equal to negative 2. So the domain of f plus g is going to be the set of all x such that x is bigger than or equal to negative 2, x is not equal to negative 1. So you find the conditions on f, you find the conditions on g, and you put them together. Those are your conditions overall for f plus g. Hopefully that's clear what's going on there. Now there's more examples in your textbook here that you can refer to, and I encourage you to do that just to make sure that you really understand what's going on here with the domain. But let's move on to the other operations that we can do and see what happens with those. So the domain, the next operation that we can do is we can do subtraction. So f minus g evaluated at x is f evaluated at x minus g evaluated at x. Same kinds of things apply here as they did to addition. So the domain is the domain of f intersected with the domain of g. So I'm just going to write domain of f, domain of g out to indicate those two domains. We take the intersection of these sets, and that gives me the domain of f of x minus g of x. One way to kind of think of this, by the way, is even though we come up with a new expression, a simplified expression for f plus g or f minus g, in order to be defined, you've really got to be able to you have to be able to evaluate f, and you have to be able to evaluate g separately. Otherwise, this stuff is not defined. So even though we come up with a new expression that maybe makes it easy to do this, strictly speaking, you have to be able to do each of these two procedures separately here in order for this to be defined. And therefore, you have to have your value for x sitting in the domain of f and in the domain of g, otherwise this doesn't work. Give a quick example here. Let's say if f of x is equal to x squared plus 3x plus 1, and g of x is equal to 2x minus 4, then f minus g of x, this will be x squared plus 3x plus 1 minus 2x minus 4. And the thing I want to note here in particular is we need to make correct use of parentheses. We've got to make sure that each function goes inside parentheses because we're doing all the operations for f first and all the operations for g first, then we're putting them together. This is important because if I didn't use parentheses here, I would subtract the 2x, but I wouldn't subtract the -4. I'd be adding it, and that would mess up the signs there. So I need those parentheses to make my signs work out correctly. Otherwise, this now becomes a straightforward combine the polynomials type of problem. So x squared, 3x minus 2x becomes plus x, and 1 minus -4 becomes plus 5. So there we go. There's our new expression. The domain is all real numbers because f and g are both polynomials, so their domain is all real numbers. And so we can simply say the domain is -infinity to +infinity. Another way of expressing the real numbers is this symbol. It's called blackboard R, and it's an R with kind of an extra line here to thicken it up a bit. The blackboard R simply symbolizes the set of all real numbers. I'm not sure if any of you have seen that before, but this is a standard mathematics notation. And depending, like if you go on and look at some other sources for additional help, you may encounter this symbol, so I figure it's good to introduce you to it anyway, even though I don't think the book really makes much use of it. So in this case, it's all real numbers. In general, though, we still just have to take the intersection of the two domains. Now, we can also multiply functions. And once again, when we do the multiplication, we're going to be getting a domain, which is the intersection of these domains. So f times g, evaluated at x, this is f of x times g of x. Once again, we can generally work out a nice simplified expression, but we do need to be a little bit careful about the domains. And I want to show you that kind of thing with, let's say that I have f of x is equal to 3x plus 1 divided by x squared minus 3x, and g of x is going to be equal to x over x minus 4. So the domain here for f is going to be, I can factor this is x times x minus 3. I need that to be not equal to 0, so x not equal to 0 and not equal to positive 3. The domain of g is going to be x minus 4 not equal to 0, so that's x not equal to 4. And so f times g evaluated at x, well, if I take the product here, this is 3x plus 1 over x times x minus 3 multiplied by x over x minus 4. And this becomes 3x plus 1 divided by x minus 3 times x minus 4. However, when I cancel these x's, they do cancel, that's fine, but we have to remember that this changes the domain of the expression. So this on the left wouldn't be defined if x were 0, even though this on the right has no problems with x being 0. So just like when we had that little issue with the addition and subtraction examples, we've got the same issue coming up here where something canceled that, see, this can only strictly cancel when x is not equal to 0. Otherwise, it can't actually even cancel it. So what we have to say here is that the domain is going to be the set of all x such that x is not equal to 0, 3, or 4, even though in this expression, the only numbers here that actually break the expression are 3 and 4. But 0 has to be excluded anyway because, you know, that otherwise, well, if we put in 0, then we wouldn't be able to evaluate f here. So that's a problem. Last thing we can do is we can do division of functions. So how do we divide functions, or how do we define the division? So f divided by g evaluated at x, well, this is just going to be f of x divided by g of x. And the domain is going to be the domain of f intersected with the domain of g intersected with the set of all x such that g of x is not equal to 0. So the problem here is we cannot allow a situation where the denominator is 0, because that would make this undefined. The problem is that sometimes when we work out the simplified expression, some stuff might cancel. So let's take a look at what can happen in this case, because I think it's worth seeing what I'm talking about. Let's suppose that I have f of x is equal to x squared minus 3x, and g of x is going to be equal to x squared plus 2x. Then f over g of x is going to equal x squared minus 3x divided by x squared plus 2x. This is actually x times x minus 3 divided by x times x plus 2. And that kind of simplifies out to being x minus 3 over x plus 2. The caveat here is I canceled these x's, which is really only valid if x isn't 0. So I need to throw out the possibility that x is equal to 0 right off the bat. Otherwise, it doesn't really work. And so what we need to do here, now in this case, the domain of f and the domain of g are all real numbers, so that's no problem. But I need to think about, where would this denominator be 0? Where would g of x squared plus 2x be equal to 0? Well, this has the solutions x equals 0 and x equals negative 2. And so the domain here is going to be the set of all x such that x is not equal to 0 and x is not equal to negative 2. So even though only negative 2 breaks the final expression, 0 is not in the domain either, because it would make the denominator 0 when we do this f of x divided by g of x evaluation. And we do have to literally do that entire evaluation there. So let me once again give you guys an example to think about on your own here for a minute. And as you're thinking about this example, I encourage you to sort of go back and look at this example again to make sure that you are kind of seeing everything that's going on here. So let's find f over g of x, both the expression and the domain, if f of x is equal to, what do we want to do here? Let's suppose that we have f of x is equal to x squared plus 3x plus 2, and let's say g of x is equal to x squared plus 2x. All right, so again, pause this for a few minutes, think about this, and then come back and we'll work it together. Okay, hopefully you've been able to figure that out for yourselves, but let's make sure that we go through it carefully and see what we can get. So I'm going to start by just thinking about x squared plus 3x plus 2 divided by x squared plus 2x. This is going to be, if I factor this, the numerator turns into x plus 2 times x plus 1, and the denominator becomes x times x plus 2. Remember, if you need to factor something whose leading coefficient is 1, you just need a pair of numbers that multiply to the constant and add to the coefficient of x. So 2 and 1, 2 times 1 gives me 2, 2 plus 1 gives me 3, that's my factorization. And now I can cancel these x plus 2's and say this is x plus 1 over x. So there we go, nice simple expression here. The domain is going to be when x squared plus 2x is not equal to 0. Well, that's x times x plus 2 not equal to 0, so x should be not equal to 0 or negative 2. So there's my domain. And again, it's obvious that x can never be 0 from this expression. The expression itself would be undefined if x were 0. But that's not the only thing that can go wrong. We also need to make sure that we are not allowing x to be -2, because if x were -2, f divided by g would actually give me 0 over 0, even though -2 can be evaluated just fine in this expression. I hope that makes sense here with this example. It's really the same kind of thing as we've encountered before a couple of times today, just in a slightly new sort of guise, a new sort of example here. Now, one of the things that you might notice is that there's this interesting thing going on, because these two expressions are virtually identical. And as functions, they would be virtually identical. The only difference is that this one gets defined at an additional point. And if you think back to the way that you graph rational functions, if you took pre-calculus here, certainly you've learned to graph rational functions, you might know that this corresponds to the case where when you graph this thing, you just have this little gap in the graph. It's going along, it gets a little white dot as a gap, and then it keeps on going. And somehow you'd really like to just fill in that gap. I'm sorry, I pointed at this one, but I meant this one. It would get a little gap when x is -2 that you'd kind of like to just fill in. It would have a vertical asymptote at 0. There's nothing we can do about that. But at -2, there's a temptation there to just fill things in. In fact, the way that you go about graphing a rational function is you graph the simplified form and then you put holes in it corresponding to those extra zeros in the denominator that you were able to cancel out. And we're going to be able to make that idea precise, in fact, by using the concept of a limit, which we're going to get to in a little bit. But one of the reasons that we want to start talking about limits is because we want to talk about under what circumstances can we do something where we just we're looking at our graph, and our graph, like, when does our graph just look like this so that I could, by filling in that gap, just make this a nice simple straight line, or not straight line, but a nice curve that I just can make with one stroke. When can I do that? Well, the concept of the limit is going to help us to be able to understand precisely when we can do that, when we can modify the function to sort of extend it like that to that point, and when we can't. Okay, so that was arithmetic with functions. Now, there's another operation with functions that we can do. Well, there's a couple. We could do exponentiation of functions. So in theory, you can also do f raised to the g of x, which is f of x raised to the g of x, but that gets to a really complicated domain. Now, we will eventually probably want to talk about this kind of stuff, but it's much more complicated stuff than the other 4 arithmetic operations. So for now, we're just going to say the domain is going to be, well, it's the domain of f intersected with the domain of g, and f of x raised to the g of x has to be defined, which it may or may not be defined, and it's complicated, right? Because when we start dealing with weird things in the exponents, then weird things can happen with whether this is really well defined. So got to be careful about that kind of thing. But in theory, you can do this. The other thing that we can do, though, which is not an arithmetic operation, is we can do function composition. Composition is actually a really cool thing about functions. It's one of the greatest things, and it comes in to play in many situations in mathematics. So let's take a quick look at this kind of function composition and what it is. So f composed with g evaluated at x means we take f and we evaluate it on g of x. And you can kind of visualize this if you think of, like, here's the function g taking one number to another. Here's the function f taking that number to another. F composed with g is just what you get if you follow this path, first doing g and then doing f. Okay, so This is kind of a nice little diagrammatic way of seeing what's going on with function composition. In fact, these kinds of things play a role. These kinds of diagrams play a role in a type of mathematics known as category theory, which studies sort of things that behave like functions and turns out to be kind of fundamental to a lot of mathematics. But unfortunately, we're not going to have a lot of time to spend talking about category theory stuff in this class. However, you guys are taking a calculus class. You may be interested in this stuff. If you want to know more about it, I'll be happy to talk to you about it outside of class and send you some resources, but it's not really going to play a big role for us now. Now, the thing is, I like to write it as f of g of x because this kind of makes it very clear what you are really doing. And just like before, we need to be careful about the domains because although we can come up with a simplified expression here, we do sometimes end up messing with the domain in the process. So the domain is going to be the domain of g intersected with the domain it's the set of x such that g of x is an element of the domain of f. Yeah, and that's it. So the point is g of x has to be defined and f evaluated at g of x has to be defined as well. Otherwise, this composition cannot be well defined. So let's just run through some examples of that sort of thing and see what I mean. Let's suppose that, first as an example, let's suppose that f of x is equal to x squared and g of x is equal to 2x minus 1. Well, then f composed with g of x is going to be equal to, I take the 2x minus 1 and I plug it into f. So that gives it squared. That's going to be 4x squared minus 2x, so minus 4x, and then plus 1. And there's my expression. And in this case, the domain is just all real numbers. There's no problems here at all with the domain. So that's an example of composition. Now, one thing to notice about composition, unlike addition and multiplication, composition is not commutative. You cannot flip the order here. So g composed with f, I'm going to use the same f and g, but if I do the opposite order of composition, this would be 2 times x squared minus 1. That's just 2x squared minus 1. These are obviously very different. So that means that this is not a commutative operation. And that's a really important fact about composition. So when you add or multiply, it doesn't matter what order you do things in. But when you do composition, it does matter. It does turn out, however, that composition is associative. In other words, what that means is that f composed with g composed with h is equal to f composed with g composed with h. Why did I write an f there? G composed with h. So, in other words, it is associative, but it is not commutative. And again, that's a really important thing about this composition stuff. Now, I want to show you why the domain stuff matters so much. Let's suppose that I have f of x is equal to x squared again, but this time g of x is going to be the square root of x. Well, in this case, when I do f composed with g of x, this is going to be the square root of x squared, which kind of looks like it should just be x, but really that's only true when x is bigger than or equal to 0. And in fact, the domain here is going to be the set of x such that x is bigger than or equal to 0, because if x were negative, then I'm not allowed to actually take the square root of the negative number unless we start working with complex numbers, and we're mostly not going to be doing that in this class. It does turn out that you can do calculus with complex numbers, but it adds some additional wrinkles. It makes it more complex, if you will. That's a truly awful pun, and I apologize, but it's actually still kind of true. So we're going to focus on the real numbers, in which case you can't take the square root of a negative, and that means this expression wouldn't be defined unless x is bigger than or equal to 0. So that's where you've got to be kind of careful here with the domain. We need to make sure, even though this comes out to just be x, the domain is only x bigger than or equal to 0. The other part here is actually usually fairly obvious. So if the output of g isn't part of the domain of f, that's usually pretty clear. I mean, be careful about it because there's probably some weird examples we can cook up where it's trickier, but usually if the output of g isn't in the domain of f, then actually the whole expression at the end, it's not going to be in the domain of the expression. So that's usually not such a big deal. Okay, so I think that covers just about everything we want to say about function composition. So what we're going to do in the next lecture is we're going to kind of do a very quick overview of graphing functions, like what is the idea of a graph of a function. Actually, we already sort of talked about that, but we'll go over a few examples of common graphs, and then we're going to start talking about where would you get the idea that limits are an important thing. Like, why do we take limits? What are limits? What are we doing? And that's going to really lead us into our first foray into calculus itself. Because so far what we're doing is more or less a review of the things that you need to know in order to motivate what we're going to do in calculus. But then next time we're going to really see specifically why we need calculus in order to understand this stuff. All right, I will upload another video in another day or two. I will see you later.